Thank you. Hi, thanks everyone for attending this introductory training on compressed air. The purpose of the training is to help the energy efficiency network and all of us in providing some background on compressed air systems and what low cost, no cost energy efficiency measures might exist. As an EVT employee, would you mind, if you're asking questions, think about this recording as being for the EEN. So if there are internal questions on let's say, tools that we have to analyze savings, that might not be appropriate for the EEN folks. I will try to help answer all questions. And if you think it is appropriate to ask, please do if you're not sure. We'll dig into the question a little bit more to understand what the nature of the question is. But you are all participating, I think, in the first recording of a training we're going to be providing on the EEN for the EEN folks. So thanks very much for attending. This should be a good presentation for those that are relatively unfamiliar with compressed air and what sort of opportunities exist. You're welcome to speak up anytime. I think Alexander is going to help manage the chat. But if you have a question, please don't worry about breaking in. Please do. I appreciate those questions. So I'm going to get started with on the agenda. We're going to go over various compressor types. Some of the things that are part of a compressed air system include receiver and storage tanks, dryers, and some of the things that you need to do to manage that system, as well as some common low-cost, no-cost efficiency measures. A couple approximations, though, that I think all of you would benefit from when trying to understand when you're getting questions, you're looking at a system. What sort of size is this system? So we see systems usually in Vermont anywhere from 2 horse up to 1,000 horsepower systems. Outside in the larger industrial Midwest, we might have 4,000 horsepower compressor systems and larger. But you can think of a compressed air system. It's compressing air and it's delivering air. It's delivering air to things that need to that actuate from the air, and about 1 horsepower of compressor can deliver about 5 CFM. So for instance, if you know you need 30 CFM to run a tool, then you need at least a 6 horsepower compressor, because that'd be 30 divided by 5. Also, we rate compressors on specific power. And generally, that specific power is in the range of about 20 kilowatts for every 100 CFM delivered. And as you're looking at performance sheets, what will go on the next slide, a really good compressor and compressor system would have a lower kW per 100 CFM. So around 17 or 18 kW per 100 CFM is great. Good is about 20 kW per 100, and not that good is 25. You will run into systems, if you meter the entire system, you can run into systems that are even worse than 25. But there's definitely, with those, there's lots of room for improvement to get it closer to the 20s and under 20. So we talked about specific power. Every compressor that's been manufactured since somewhere around 2000 should have with it a performance data sheet. So that's what we use in evaluating the performance of these compressors. And as you can see on the slide, we have an Atlas Copco. We have 2 different CAGI sheets. It's the Compressed Air Gas Institute sheet. They're sometimes well documented in a vendor's website, and sometimes it's hard to get. the best is to get it from the vendor who sold the compressor, but we can help find the CAGI sheet for any of these compressors and help you analyze the performance or look at the performance. But as you can see on the compressed air sheet, on the bottom, it'll show on average what is the specific power. So you can see this left one, a fixed speed compressor from Atlas Copco. It's got a 17.1 kW per 100 CFM. That's a good compressor. You look over here, and this CAGI sheet is for a variable speed compressor. The difference you can see is that it has kW for different capacities, and then it rates that specific power based upon the part load efficiency. And you can see that we've got a specific power a little bit higher than the 17, around 19.5 kW per 100 CFM, all the way up to 25.5 kW per 100 CFM. And there's a reason for that. When you put a variable speed drive onto a motor, immediately you have something in the way. It's a control system that's got to eat up some electricity. So in and of itself, it's already reducing or increasing the power output or power need of a compressor. That can be a good thing when it's a variable speed drive on a modulating system, and it can be a bad thing when you've thrown in a variable speed drive and you just run it at 60 hertz all the time, 60 hertz being 100% speed. We'll go a little bit more into that data, but here we have, I'm going to go over the compressor types. We just saw CAGI sheets that are for a modulating screw and a variable speed modulating screw, but the general compressor types run in from reciprocating compressors, rotary screw compressors, and then the bottom three are less common: a rotary vane, a scroll, although those are very common in refrigeration, and a centrifugal. And we're going to go through each one of those types and talk about some of their pros and cons. First is the old standby, the reciprocating compressor. It is by definition a positive displacement compressor. In other words, it's just pushing air out of the piston. That amount of air volume in the piston does not change. Its output is how much volume is in that piston chamber. It's not like a centrifugal fan or a centrifugal compressor, which would be a centrifugal system, not positive displacement. They're usually smaller in size, 25 horsepower and less. Again, until you get out to the Midwest, when you have some of these large auto manufacturers that have giant reciprocating compressors. But for the most part, we're going to see smaller reciprocating compressors, 25 horse and lower. They're usually close to the point of use. They're very simple to maintain, and they provide nearly a 1-to-1 power to output ratio. And they're almost always put on load, no load control. And that just means when the system is losing pressure, the compressor kicks on. And when it needs pressure, the system, or when it no longer needs pressure, the system cuts off. But 100% of the possible air coming off of the compressor is fed into the system at that time, during that on-off time. This is an example of the nearly 1-to-1 ratio. We have flow capacity on the bottom axis and power on the y-axis. You can see that the red compressor is a single stage compressor. I'm sorry, a two-stage compressor. And for the most part, it is 1-to-1. You see this linear line. It's rather a gentle slope. And as you increase flow, you also increase power by about the same amount. In the green is just a comparison of what a variable speed screw compressor has. And it's almost identical, but you can see that the reciprocating compressor almost matches what a variable speed compressor does. And we've had many folks ask, well, can I get a rebate on a small variable speed compressor? Because I think that you guys want us to get that instead of a reciprocating compressor. And for the most part, you would be better with a small reciprocating compressor than paying for the additional cost for the rotary screw that has a variable speed. The reason why reciprocating compressors are dominant in about the 25 horsepower and less, but the rotary screw is hitting the larger market, is that a reciprocating compressor, although it's efficient, it can be very loud and produce vibration. As you get larger and larger reciprocating compressors, you get louder and louder systems, and you have a lot of vibration, and you end up having to engineer a footing to hold that compressor down so it doesn't vibrate the whole site. So when manufacturing became, when tolerances of manufacturing became really good and got better as we got smaller on systems, the rotary screw compressors have started to really take out the reciprocating compressors in the larger horsepower, because they're not anywhere near as loud, and they are not anywhere near as causing so much vibration. So they're a lot easier to put into a plant that needs a high horsepower compressor. Although you can see the reciprocating compressor is very efficient. So I would never want someone to think that getting a rotary screw compressor on a variable speed is better than getting a reciprocating on the energy side. It might be better for other things like noise and vibration, but it may not be better for you on efficiency. Rotary screw compressor. For those that will be able to watch this on the EEN, you could hit that YouTube link, and it will show you the actual action of these two rotary lobes that you see in the bottom left. I'm not going to do that for this presentation because I'm a little nervous of getting onto the web and then getting back to the presentation while on Teams. So I'm not going to do that. But as you can see, this rotary lobe, you have two screws. One is a stationary screw and the other one is a rotating screw. And all it's doing is moving air along the volute of these screws from a larger to smaller volume, and that compresses the air. It's a positive displacement, just like the reciprocating compressor. And you can get oil contact, oil-free, water-cooled, or air-cooled screw compressors. The most dominant are what you see in red. That's the oil contact and air cooled, meaning oil is lubricating the mating surfaces of these two screws. It's also allowing or helping contain the air between the two screws so it doesn't bypass around the screw. And they're air cooled, meaning they're not water cooled or some other fluid. As you can imagine, it's a lot less complicated to buy an air-cooled system than a water-cooled system because you don't need to feed water to it. However, water is better at removing heat, and most water-cooled compressors are more efficient than their air-cooled counterpart. Oil-free is if you are not using an oil in the mating surfaces, which means that the tolerances of the two screws, the mating of the two screws, is extremely tight, which increase costs of the compressor And it also increased some of the power need of that compressor because you are starting to do, you have a lot more friction. You choose oil free often in the food industry. You can get food grade oils for oil contact, but we have been seeing more and more for beverage manufacturers and food manufacturers that they will choose oil free because there is no possibility of oil getting into the food that we're eating, and or even if their process was, there was a positive barrier between the oil and any food. So for instance, if they're just using the oil screw compressor to run a packaging machine to wrap boxes, let's say, clearly that oil is not going to be touching, if there is oil in the air, it's not going to be touching the food. It's just going to be maybe getting on the carton. But for their marketing, if you will, they might choose oil-free 100% so that they can guarantee to their purchasers that there's no possibility that oil is getting into the food. A rotary screw, like I said, they've starting to become rather small in size. I've been seeing compressors, even rotary screws that are down around 5 horse. I have 15 on the slide, but I just saw one that's 5 horse, up to 300 horsepower and larger. They're usually part of a central system. They might not be just a spot use. They are quieter than reciprocating compressors. They have much less vibration. And they really are the largest market share of all compressors. They can run on load, no load, or modulate. The benefit of a rotary screw compressor is that it can modulate the amount of air it puts out, as opposed to the standard load, no load. And that can be advantageous depending upon what your plant needs are. Load, no load, again, is just 100% CFM output and then off, whereas a rotary screw can have 70%, 30% output and then off, or 30% rise to 40, 50, 100, and then go off. You can have them in fixed speed, meaning they're always cycling at 60 hertz in the US, or they're variable speed, which we will talk about the efficiency side of a variable speed. A variable speed rotary screw is typically much more efficient than a fixed speed if you need that flow modulation. Here's a couple shots of the variable speeds. They are often just compartmentalized. The compressor is actually in the chassis, and the variable speed is integrated into the chassis. A modulating fixed speed versus variable speed graph. On the bottom, we have capacity. So that's the output of the compressor going up to 100%. And then the amount of power that these compressors use. The green is a variable speed rotary screw compressor. The red is a fixed speed rotary screw compressor. And as you can see, a fixed speed compressor, it does not turn down, and it has a very flat curve. Turn down on power, I should say, much. It has a very flat curve. So if you are close to 0% flow output, it's still consuming about 70% of its maximum power. This is why using a variable speed on the rotary screw can be a large energy saver. But if you're only using the rotary screw to put out 100% of flow, and it's in load, no load, you would likely rather see a fixed speed compressor, because we're going to go over this in the next couple slides. This region here, the variable speed will actually consume just a hair over what the fixed speed would do at 100% speed. So it's all dependent upon what your plant needs. If you need a variable flow, using a variable speed would be better. If you need a 100% flow and it's on load, no load, you probably are better suited with having a fixed speed compressor. Examples of a head-to-head comparison for an Atlas Copco 120 horsepower fixed speed versus variable speed. This is the same that we had before. Again, we're looking at the compressed air data sheet, or the CAGI sheet, most people call it. These are both air cooled. And we've got the different pressures and flows. This variable speed can produce 570 CFM at 100% power. This one produces 576 CFM. The total package input to produce 576 CFM is 98.6 CFM. You can see here, the total package input to produce just a little less flow is higher, 117. So if you wanted to run a compressed air system on load, no load, you might consider not putting a variable speed on it because you do sacrifice some kW. But what's the magic of the compressed air, the variable speed compressed air? That's what we're going to go over next. This is where it can really save energy. So if we look at the same compressors modeled over their power use and flow, again, that Atlas Copco variable speed at 100% flow was 111, pardon me for that, 111.7 kW, whereas the fixed speed was 98.7 kW. But if you are putting this into modulation, the fixed speed, you can see at nearly zero flow, you still have to consume 69.2 kW. The variable speed, however, once we get below about 80, it looks like 82, 83% flow, there's a drastic drop, and it's that close to a linear drop of kW per CFM. And this usage along this range saves the energy that's in this area right here. And that can be a lot of power and savings for a customer. You can, again, looking at the specific power, although the fixed speed had a better specific power, it was at 17.1 at full speed than the variable speed. The variable speed is almost always sitting around the 20 kW per 100 CFM, whereas as you back off on the flow rate, this rises significantly up to, frankly, it's infinite once we get to zero flow, but we're 140 kW per 100 CFM. So again, this is why if you're modulating your compressor, you'd rather have it be on a variable speed drive. So just a recap, for rotary, you have oil or oil-free. Oil injected, the tolerances are a little larger, a little less energy use, costs a little bit less to buy the compressor, and it costs a little bit less on power. But if your business needs once the oil-free, you're going to have to pay a little more in power. It usually costs quite a bit more on the actual compressor itself. And there's more wear on the compressor. It's just inherent with it. Just an example of oil-free versus oil injected, showing you the same variable speed compressor that's oil injected versus oil-free. And you can see that this has less air capability and a higher kW use for the same chassis. So this just gives you an example of what sort of sacrifices you might have to make to go oil free. Some other compressors. We've been seeing some manufacturers of beverages, let's say a couple breweries, looking for oil-less or oil-free compressors, but they may not need a large compressor system to run their bottling or canning line. So there have been some manufacturers that have bundled scroll compressors together. And you can see on the top left, we have the green things are motors, each driving a different scroll compressor. It can go from 5 to 50 horse. It's usually a multi-stage compressor. So one stage comes on, the next stage comes on after that and following. And one of the neat things about this is what's been attractive to some of these folks is that if one scroll goes down, you don't lose compressor 100% of your compressor capacity. You still can limp on until you get a new compressor. These are pretty efficient because they're staged. They're a little bit more like a variable speed compressor. They are, from what I understand, quite expensive, but they're in the marketplace and you may see them. And they're not a bad choice. I know Switchback Brewery has one, and Caledonia Spirits in Montpelier has one. Another compressor is this Hydrovane manufacturer who makes rotary vane compressors. And a rotary vane compressor, although it looks a little bit like a centrifugal system, we've got an impeller and it rotates, and you might be fooled to think it's a centrifugal compressor, but it's not, because it's got a little bit of, it's off center here. So as it rotates, sucks in some air, and that air travels around here, it then gets into a smaller output, smaller volume, and out. So it's a positive displacement. It's compressing by just making the area or volume smaller. I have not seen any of these. I have heard a few dentists have them. I imagine they're pretty quiet and pretty effective, but we don't see many of them, and they're pretty small when I've looked on the web to find some. The next type of compressor is a centrifugal compressor. These can be very large. The one that you see, the old one, that's a 4,000 horsepower centrifugal compressor running an air plant in New York State. Centrifugal compressors can provide an enormous amount of air for a lot less power than a rotary screw, but they need to be operating at a rather steady output all the time because they're very expensive. So first you need to think of the cost effectiveness of buying one, but you don't get much of a turn down on these before you start having some severe problems with them. So they're best suited for almost 100% load 100% of the time. And they're used in Vermont primarily at our ski areas. I don't get to see many of those. A couple people on our ski team do. They're fascinating to me. But when we go over low cost, no cost measures, all of those would apply. But if you get to work on a centrifugal compressor, you're going to be working on a large system, and large meaning hundreds, if not thousands of horsepower of compressor capacity. So a typical setup for a compressed air system, you can just see the caption. We've got an air compressor, an air tank, or what we would call a receiver or storage tank, a filter before and after something called the air dryer, and then filters after that. So those filters, they're helping get rid of particulates, maybe some airborne moisture, and also oil, both after the air tank and then after the air dryer. There are better filters than others. Some have high filtration and high pressure drop, which would not be good. Some have high filtration and low pressure drop, which would be great. And some are just mediocre, but for the most part, you will see these installed, and hopefully they're installed correctly. Often we've seen or heard of them being installed backwards, and they don't do the filtering, they just provide the pressure drop. So the receiver storage tank. Smaller systems, you may not have a tank at all, or it would be part of a package. So the bottom left is a packaged one, very common. The garage one I have at my house has a small receiver tank, but you don't have to have a receiver tank. We'll go over that. The larger systems, the receiver tanks are not part of the compressor package. They're often separate and huge. I think that one there on the right is about 3,000 gallons, maybe larger. And there could be multiple ones, and sometimes they're configured one before the air dryer, and they might call that the wet tank. We'll describe that a little bit later. And then the one after the air dryer would be the dry tank. But they're both serving a purpose, and we're going to go over those purposes in a second. Can a receiver tank add value? Obviously a receiver tank costs money, but it's been said that you can never have too much storage. The reason why it's pretty handy is it can provide nearly instantaneous air. Suppose you have a system that is off, the compressor is off, and all of a sudden you need more air that's in the lines. That compressor has to cycle on to feed that quick need of air. And without a buffer tank, you're not going to get it when you need it, because the compressor has to first get the signal that it needs to be producing air. It needs to turn on, and it needs to start getting up to pressure to then deliver the flow to that demand. So it really helps on systems that have short, quick uses of air. It buffers a system, making it a lot more stable. So you don't have, with a receiver tank, you really do help prevent a compressor from cycling on and off or short cycling, because I've seen many where the air demand is fast, the compressor kicks on, but the air demand is done by the time the compressors got up to speed and start delivering air at the right pressure, and then the compressor just kicks off. So it really did no work, useful work, to provide that air. It can help increase efficiency, but be careful, that depends on control. So don't want to get too deep into the operations of all these different systems, but sometimes adding a receiver tank is not going to save energy. but it certainly is a good idea to have on a compressed air system because of all of its other benefits. They're especially useful when you have air actuators that need a lot of air for a short period of time, packaging systems that also have air actuators or blow open bags very quickly, CNC machines that often have various needs for compressed air in short cycles, so they might have a quick, fast burst of air to clean the electric or clean the chip tool that's on the CNC machine. And a compressor just can't cycle on fast enough to meet that demand. So a storage tank is extremely useful. I want to talk about air and water. First, I'll say if you're compressing air, you're condensing water. This graph illustrates the point. I couldn't find a graph that showed me in British units what I wanted to illustrate, but I have it annotated. So at standard atmospheric pressure and different relative humidities, 50 to 80%, the dew point here on the left is, let's say, 20 degrees, which is close to 70 or lower. So we're not getting condensation at atmospheric pressure. But if you double atmospheric pressure or quadruple or at 100 psi, which is about the range that you're running a compressed air system, you're up here close to in the range of 120 degrees is the dew point temperature. And that's just simply saying if the temperature of the air is below or hits anything that is below 120 degrees, it will drop moisture out. And all of our systems eventually are hitting something that is less than 120 degrees, and so you get moisture. So you need to dry the air most often when you're using a compressor for manufacturing plants. In some garages, you don't need it because your air tools can handle a little moisture. But if you're using a compressor a lot, you will be producing a lot of moisture, and you need to manage that moisture. One of the ways to manage that moisture is air drying. So remember that screen, we had a compressor, a storage tank, and then an air dryer. For most applications, the air dryer is just a refrigerator. It's a dehumidifier. Some applications, it can be a desiccant dryer. In other applications, it can be the heat of compression of a compressor can help do the drying, or you don't have a dryer at all. We're going to go through the first two being the most common. And by far and away, the refrigeration dryer is the most common. The one efficiency penalty that you have on most refrigeration dryers is that it's a dumb system. It's designed to drop out moisture at a 90-degree day with high relative humidity all year round. Well, we don't have 90-degree days with high relative humidity all year round, but these systems, the compressor operates as if it is always trying to remove moisture and a lot of it. So they're called non-cycling refrigerated dryers. They don't cycle on and off. They're just on all the time. An efficiency gain is to get a cycling dryer. The cycling dryer cycles on and off depending upon the moisture content of the air. That can save a lot of energy because you're not having a compressor running 24 hours a day, 7 days a week, or if you're only using the compressor during a day, then just the 8-hour a day. But the cycling dryer, it cycles on and off to reduce the moisture, and it's not running all the time. They might call them high mass systems as well. So you may hear them as cycling high thermal mass systems. Efficiency Vermont provides incentives for getting a cycling dryer. A desiccant dryer. Let's think about why there might be something other than the refrigerated dryer. If you have refrigerated dryer, it's condensing water and then expelling water. If you're outside in the middle of winter at a, let's say, rock crushing plant, unless the dryer and its drain is not going to hit 32 degrees or below, you're good. But if it's outside, exposed to the elements, you will create ice cubes and it will not work. So you need to choose something other than a refrigeration system. And therein lies the desiccant system. It doesn't create condensate. It absorbs moisture out of the air. And they can be run at very low dew points as well. So often, even if you're not trying to prevent freeze-ups with condensation, if your manufacturing process or the site's manufacturing process needs a very low dew point, meaning very little water in the air, you might use a desiccant dryer. Packaging companies, let's say, that make Kool-Aid, they might use a desiccant dryer, because if you have moisture in the air and it gets into the Kool-Aid package, that Kool-Aid turns into crystals before it gets into the cup. So low dew point is very good for certain packaging systems. It takes more energy than a refrigeration dryer. Even a standard non-cycling refrigeration dryer uses less energy than a desiccant system. But as you can see, they do provide a very good benefit if you're worried about freezing or you need a low dew point. The way they operate is that they're usually in a 2-tower system. One tower is in the act of absorbing moisture, while the other tower is being regenerated or dried. And the towers switch between each other on typically a timed cycle, but not necessarily only timed. It can be based upon the moisture level in each tower. But the way it dries itself or regenerates itself is it uses compressed air. And as you can see, this one on the left is being regenerated. A little air from the compressor system is diverted to this tower. It picks up the moisture and then is expelled. While this one is getting moisture off of the compressed air system at the same time. Expelling compressed air is inherently inefficient because you're not doing work with it except for drying the tower. And again, with the non-cycling refrigerated dryers, there are the common baseline desiccant dryer is not smart. It's on a timer. It regenerates whenever the timer says it's time to regenerate, and not when the tower actually needs to be regenerated. And therefore, it's expelling air, usually 15% of the compressor capacity, all the time. There are more efficient options with the desiccant dryers. Those options could be, it has a sensor in the regeneration, or it has a sensor for both towers to regenerate when it becomes saturated. And then it expels the air. Or instead of using compressed air, it might use air off of a blower which hasn't been compressed to 100 psi, but to it's really not much psi at all, which takes much less work and energy to do the drying. And in those cases, it might actually have an electric resistance heater, but an electric resistance heater with a blower, in this case, is a lot more efficient than using compressed air to do the drying. But get back to that slide on air and water, because now we're going to move into condensate removal. Remember, almost any time you're compressing air, you're creating liquid. And at some point, that liquid is going to need to be removed. And it's going to be in various places of your compressor system. So every compressor has a condensate drain. Every tank has or should have a condensate drain. And every dryer, refrigerated dryer, has a condensate drain. Here's a tank. And someone at one point ran into the problem of someone closing that valve because the condensate drain had been closed. It likely filled up that tank, and instead of getting air out of the tank, you got water. I'll tell you a short story. I was at a manufacturer. It was a startup. They didn't know compressed air systems well, and that's to no fault of their own. They knew their business better than the mechanical systems, and they had a receiver tank. And one of the complaints they told me about when I visited them was that they're starting to get this water in their air. And it was just a small reciprocating compressor with a tank under it, much like you see in a typical garage shop. And I asked them, I immediately saw that there was nothing coming from the bottom of their tank. There was a little nipple at the bottom of the tank where you can open the tank or attach a drain, but that nipple had remained the same paint as when it was brand new. And I asked them if they had ever drained their tank, and they said they never knew that they needed to. So I went over to the tank. I'm not a big person, but I was big enough to be able to just shake the tank a little bit, and it was probably 3/4 full of water. So they've lost a lot of their storage, but also they've been just collecting a lot of water. So you have to get rid of water. And often, for most systems, you will see a drain that is like the one on the left. It's a time drain. And on the right are what are called zero loss drains. A time drain, that is by far and away the most common. And as you can see, you have two settings. The one on the left that says seconds is how many seconds that drain remains open. And on the right is how many minutes that drain opens, or how the period between opening and closing. So you can see it's every 0 to 45 minutes, you might be able to dial this thing to just open. It doesn't know whether or not there's water. It just opens, and it opens for so many seconds, regardless of water present. And once water is no longer present, it's still open for the amount of time that you've set it. And that opened part is expelling air, not water. And you just compressed all this air to 100 psi to then let it go out a drain. On the right are zero loss drains. They have floats in them. They cost more, but as the float recognizes it, now my bowl is full of water, it allows the air pressure to push the condensate out. But just before all the water is expelled, it closes the valve again. And it cycles on and off depending upon the moisture in the air and how much is condensed, as opposed to just this timed drain. And zero loss drains are an extremely cost-effective measure because you're not wasting air. So we're going to go over some low-cost, no-cost measures. First up, replace the time drains with no loss or zero loss drains. I have an example here. I have a time drain that opens every 5 minutes for 3 seconds, which is what I see a lot of. That costs that site about $1,200 a year to operate. A no-loss drain costs, you can see I just pulled this off of Google yesterday, anywhere from $400 to $900 or $1,000, depending upon the size of the drain, the manufacturer, and some of the extra benefits of certain drains versus others. Some are plastic, some are metal. But I'm sorry I don't have the comparison. I thought I did. These no-loss drains, if they're not consuming $1,200 a year in lost compressor capacity or compressed air, then, and they cost less than $1,000, you have less than a 1-year payback for replacing these drains. Inappropriate uses. Now, in the efficiency world, we sort of we use the word inappropriate use, which seems like it's a bad thing to do. It's not a bad thing to do. It's just a very costly thing to do compared to other alternatives. So those things that we would call inappropriate use or very costly uses of air that you could do for a lot cheaper are things like open blowing and sweeping. I think I've seen many, and I bet all of you have, many places where you see someone with a long air wand and they're blowing dust, they're sweeping the floor with their compressed air system. And that's very effective, but it's extremely expensive to do that in running that compressed air system. Other places might be using compressed air to cool personnel or electronics. Actually have nozzles pointed at people to just provide some airflow. Compressed air is very easy to get around and use through your plant, but it's extremely expensive to produce. And most people don't realize how much it costs to produce that compressed air, so they don't realize how much it's costing to do the shortcut of just using these compressed air for these inappropriate uses. Another inappropriate use is sparging. And what I mean by sparging is, let's say you have a bath, you have a water bath or a chemical water with glycol or ethylene in the bath to help do a parts washing. And using compressed air, you just hook up the compressed air system to the bottom of the sparge bath, and that helps agitate the water and helps clean the part. But you have 100 psi of air doing the sparging. And every psi is equivalent to a little over 2 feet of water. So you have 100 psi, which you could be able to sparge a 50-foot bath versus a bath that's usually only 2 or 3 feet deep. A blower can do 2 or 3 feet of sparging a lot more cost effectively than a full compressed air system that, remember, you've also dried that air and then you're putting it into a wet bath. Mixing is another part where you might use a compressed air system to do mixing, whether it's using the air to actually do the mixing or mechanically the air is driving the mixer. There's a lot of energy that's going in that compressed air, and there are great alternatives. And then parts movement. Often you might see at the end of a parts line or packaging line, if something's underweight or under spec or doesn't meet spec, there's just a nozzle and it blows the part off of the assembly line. you typically don't need 100 psi to blow a part. So that parts blower is pressure reduced down to, let's say, 20 psi or 10 psi or less, but you've compressed it to 100 psi and spent all that energy doing so. Some alternatives: if people knew how much it cost to do that air blowing of the floor, there's several people's worth of salary that could be used to do the sweeping. You can use brooms, you can use blowers or good old vacuum systems. For cooling, an air conditioner is a lot more efficient at cooling than a compressor, a compressed air system, or blowers. Sparging or aerating tanks, blowers. Mixing, use mechanical mixers or blowers. Mechanical mixers being attached to an electric motor, not a compressed air system. And then parts movement, you can use blowers or electric or hydraulic actuators. So those are examples of inappropriate uses. Engineered nozzles. Let's imagine that inappropriate use of sweeping, or you do need compressed air. Compressed air does a fabulous job of removing grit and dirt and dust off of parts. You will often see a shop-made nozzle. It's usually out of 8-inch copper. And to run it, let's say for just an 8-hour day, and you run it in total, you blow this part off 1 hour a day using 80 psi. To operate, it costs $509 a year. If you buy this Xair 1102 mini super air nozzle or other engineered nozzles for $35 off of the web, or certainly cheaper from your supply house, the payback is enormous. The cost of its use is $73. It costs $35 to buy, which means the payback is 21 days of use. This is an extremely low cost, no cost measure. Another low cost, no cost measure is reduce your pressure. If the compressor is rated 150 psi, it doesn't have to run at 150 psi. You want it to deliver what your air needs are. And certainly if your air needs are 90 psi and you put it at 150, you might get the air the pressure you want, but it's coming at a cost because that compressor is doing so much more work to go from 90 psi up to 150. And in fact, for every 2 psi you reduce the pressure that compressor is producing, you gain about 1% on efficiency, and you actually get more cubic feet per minute for the delivery of from the delivery of the compressor. If you look at those CAGI sheets, you can see that you get more air at lower pressure. So 125 psi compressor rating, let's say it produces 100 CFM. If you ran that compressor at 150 psi, instead of 100 CFM, you might see that it can produce 90 CFM at 150. So if you're really needing air, you're not needing pressure, you're needing air, and reducing pressure is a great idea. And often we tell people it's a little bit like operating a home thermostat. You turn it down in increments until there's a problem and then bump it up again. So if you're at 150, your air tool, your grinder, let's say, needs 90 psi. And of course, you need to get 90 psi from the compressor all the way over to the grinder. You do need more pressure than 90 to feed that grinder. But could you get away with 95 instead of 120? Could you get away with 100 instead of 120? Just keep dialing back that compressor pressure until you're comfortable or you start getting complaints, and then dial it back up. But very, very often, you do not need the full capacity of that compressor, and you do well by reducing the pressure. Heat recovery. We kind of ignore this all too often, even in the work I do. As you can see on the graph on the right, it's called a Sankey diagram. And on the left is all the energy that's put into the compressor. And then out is how much energy is going to what. So we've got some on leaks, some on what's called artificial demand. I can go over that in a little bit, but that's not as important. These inappropriate uses, and then high value production. That's why you really need that compressor. And then 80 to 85% of all the energy that went into the compressor actually turns into heat loss or heat energy. And that heat energy is often easily recaptured. And you can see in this diagram, it's just some simple ducting, a thermostatically controlled vent, and maybe a fan. So here we have a compressor. That's a CAGI compressor. It's pulling air in. During the hot summer, it would be expelling, or if the plant doesn't need heat, it's expelling out. That's usually the default. It's always expelling out. Or you can recapture that heat and deliver it to your space. That's a very low cost, no cost measure. Another one is fixing leaks. So the DOE estimates that for all compressed air systems out there with distribution systems, there's an average 20 to 30% leak rate. So if your compressor is designed to be putting out 100 CFM, it could potentially be leaking 30 CFM of that 100 CFM. So finding and fixing those leaks can be very cost effective because those leaks are providing no value. It may also be causing you to think you need a bigger compressor because your compressor can't keep up with demand. And if you fix the leaks, you might find you don't need to buy a new compressor, you just needed to fix those leaks. And here are some examples. Ironically, if you have a fixed speed compressor, fixing leaks is less effective than if you have a variable speed, but they're both very effective. But I'll go through this. Let's suppose you have 2-shift operation working 5 days a week. And that 90 horsepower compressor that we had from the Atlas Copco was running about 80% or 400 CFM all the time on average. And you do a leak detection audit, which could cost, depending upon the size of the system, anywhere from $1,000 to $5,000, let's say. And you find 20% leaks, but realistically, some of those leaks you just can't get to. They're in the machine. It's very difficult to take that machine apart. So let's say realistically, you can only get to 60 CFM of the 80 CFM that's being lost. The savings for the fixed speed is about $1,700 a year. So you spent, let's say, $2,000 on the audit, another $500 on the repair. That's just more labor and maybe some good sealant. So you're in for $2,500 to do it, and it's saving you $1,747 a year. You're getting less than a 2-year payback. On a variable speed, the reduction is more dramatic, and the savings is almost $7,000. I just want to go over why the dramatic difference, and why, if you have a fixed speed modulating compressor, maybe leak repair is not the lowest cost measure, but it's still a good measure. The problem is, this is that curve. and it's very flat. So if you're reducing the flow from, let's say, 80% to 60%, the savings is just 3 kW. Because again, this thing performs relatively poorly throughout its entire flow regime. So fixing leaks on a fixed speed modulating screw compressor isn't as cost effective as if it's on a variable speed compressor, because as you can see here, if you go from about 80% down to 60%, it's a much faster drop in kW. In fact, it's 12 kW of savings. So that 12 kW, 2 shifts a day, 5 days a week, generates about $7,000 of savings. So we talked about the low cost, no cost measures. Efficiency Vermont is fully in support of all of those, but we do have prescriptive measures, and this is meant for most of the smaller systems, but they apply, generally we can apply these to the larger systems as well. For having a variable frequency drive on a screw compressor, we pay about $150 per horsepower. Well, we do pay 150, not about. For air receiver tanks that are on systems that are controlled in the load, no load, that is 100% on, 100% off. The storage tank does save energy in those cases. And you can see the different tank sizes. This is the compressor horsepower. This is the tank size in gallons. And this is the rebate. So if you have a 1,000-gallon tank on a 35 horsepower compressor, we could reimburse or rebate $1,300 of that. And then for those cycling refrigerated dryers, we have a prescriptive rebate for those depending upon the dryer capacity. And you can see it can range from $100 to $350. And these are tiered to be about half the cost of the upgrade for the cycling. So too is this. 150 per horse is almost the cost of the VFD itself. And then for those no loss drains that had less than a year payback, we provide a $100 rebate. And for the larger systems, we do custom projects with many folks, and we will work with you on those as well. That is the end of the slide projections, but do we have questions? I'm going to go over to the chat feature to see if there's any questions here. So far, no questions. I sure hope all of you have been hearing me this whole time. I assume you'd be speaking up if you haven't. But are there any specific questions from anyone? Awesome. Thank you all for attending. Thank you to the Energy Efficiency Network for letting this recording happen. Oh, I have a question from Chuck Parisi. Not sure why all of a sudden I'm echoing. Sorry about this. Do you have any commentary on compressed air system monitoring? Oh, thank you, Chuck. You probably had to mute. Yes, compressed air system monitoring. If you're not measuring how much flow you need, especially on the larger systems, or how much flow the compressor is using, you really are running blind. And we can help support a compressed air flow meter. And for the more complex systems, flow meters and power meters and pressure meters can be supported, but it's on a case-by-case basis. But if you have a large system and you're not monitoring it, then you really don't know what that system's doing. You're just hoping it's working. And often we found with compressed air monitoring that problems arise. a company might think they need a new compressor, but if they did the monitoring, they might find that they don't need a new compressor. They just need to do some changes to keep that compressor running well, including getting rid of the leaks. Michael Sox is asking if there's any maintenance benefits of screw versus reciprocating compressors. Yes, rotary screw compressors run for many, many, many thousands of hours with little maintenance required. They do need to be maintained, but they need less than the reciprocating compressors. As you can remember, those reciprocating compressors are vibrating a lot. So inherently, they're subject to more maintenance requirements than the screw compressor. So it can be justified to get a screw compressor over a reciprocating compressor if you're putting a lot of hours on a compressor. Seeing if there's any other questions. Oh, Michael also added that a screw compressor typically can hold a steadier pressure. It has a more stable profile in its output in pressure than a reciprocating compressor. So if you do find that you need a very steady pressure and flow profile, a rotary screw could perform better than a reciprocating compressor. All right, as there are no more other questions, thank you very much for attending. I hope you learned something. I always enjoy giving these presentations, and I hope the Energy Efficiency Network can find high value in this. Thanks again.